Good morning, everyone. Welcome to this session on week 3. Happy Wednesday. It's 10:10 here in Pullman, and most of you are, I know, here, and wherever you are, it's also 10:10 in your time, I'm hoping. So we're going to get started today, and I wanted to use all of our time to finish up the discussion we started last time, and then accomplish quite a number of things. And so I know people are joining, and I have waited for people to be able to join, but I posed a question, and it's going to be a very quick one on the group chat. And if you have seen people answering, the question we have is this. So you have noticed that we are now in week 3, and right in the middle of week 3, in fact, on a Wednesday. And so we might have seen how things have changed. There was a little bit of an adjustment in the beginning. And so by now, I think we have established a routine. And so I'm just curious in terms of how much sleep you're getting compared to how things were before. There are a number of factors. It's not just about having things to be online. There are other things too. But just generally speaking, are you sleeping more? Are you sleeping less? Or are you sleeping about the same? That's the question that people are responding to. So if you feel like participating, that would be great. And so I'm going to get started. Just so now that you know the questions, you go ahead and answer. And I know we are still joining. There are more people coming. And so I would hope that it will be on time, but this will be recorded, of course, and it is going to be posted afterwards, and make sure that you check out on that one. So undecidability is the topic we're discussing. And we began this on Monday, and therefore it is part 2 today. And so I want to get started there, and so let's move on. So what we saw in the last lecture was began to look at a big problem, and a big problem that is undecidable. And we began by having to define the language. And we have had a series of formulations of problem around DFAs and around context-free grammars. And so the subject we had the last time we started looking at a problem in this class of Turing machines was ATM. A is for acceptance, and the TM is for Turing machine. So we have a Turing machine M and a string W, and the language, the membership language, the language that we're considering is the set of all languages where M is a Turing machine and M accepts W. So that was ATM. And so we began, and we motivated the whole idea of having to say that this is undecidable. But we showed last time that this problem is Turing recognizable. And the tool used for that one was look at universal Turing machines, which is a way to say, I have a Turing machine. As long as somebody else gives me a specification for any Turing machine, that universal Turing machine will be able to simulate it. That was the underlying idea there, but we showed that ATM was Turing recognizable. The other thing we did last time was look at what Cantor's work was, and look at sets that are infinite in size potentially, and a way to measure their size. And so we distinguish between 2 types of sets that are called countable and sets that are called uncountable. And we use the set of natural numbers as our device to determine whether something is countable. So we know that it is infinite in size, the set of natural numbers. But if we are able to determine a correspondence, that's a keyword there, a correspondence between the set of natural numbers and a set that we're considering, then we will call that set countable. And correspondence means there is a one-to-one and onto function that maps every element of the set of natural numbers to every element of the set that we are looking at. When that is not possible, then that set is called uncountable. And we saw one good example of an uncountable set, and that was a set of real numbers R. And that was done through a method called the diagonalization method, due to Cantor. And Cantor was an 1870s mathematician. We looked at his picture and looked at a little bit of his work and the philosophical things around it. So the diagonalization method was important. So it's, I think, not only what we just did, but also the underlying thing that I want you to carry with yourself and be able to tell somebody, so keyword universal Turing machine that enabled us show ATM is Turing recognizable. Keyword correspondence, one-to-one function and an onto function that helped us to show whether a set would be countable or uncountable. And as I said last time, as weird as it sounds, there are infinite sets which we consider countable, like the natural numbers. And we found out that the positive rational numbers are countable, whereas the real number is not. And the diagonalization method, we constructed a particular kind of X to demonstrate that this would lead us into a contradiction, and that was the diagonalization method. What we want to do today is 4 things. The 3 are going to be on this topic, and the 4th one you will hear me say. I'll save 5 minutes towards the end to talk about it. So the first thing we want to do today is to show that, generally speaking, there are some languages that are not Turing recognizable. Try to picture the kind of containment class diagram we saw. We've got the regular language, we've got context-free language, and we had decidable language, and we had Turing recognizable. And so we had these 4, and so they were contained the way I told you about. And so it might be interesting, and you probably have maybe wondered if ever there would be something outside of that big circle. Languages that are not Turing recognizable, and they exist. So the first thing we will do today is just show that there are some languages that are not Turing recognizable, generally speaking. The second thing we will do today is the thing that set the whole thing in motion for us, that ATM is undecidable. We made that statement, we just declared it, but today we'll prove it. And so that will be the second thing we'll do today. A good portion of the time will be spent doing that. And then we'll come back and exhibit one specific example of a language that is not Turing recognizable. So the first point says there exists. There are some languages that are not Turing recognizable. We just say general statement. And then we'll say, here is one concrete example of a language that is not Turing recognizable. That will be task 3. So count me accountable for this one. We'll go through this and make sure that all 3 of them are done. The last thing we want to do is we have an upcoming midterm on Friday. And so I'll use a few minutes. There were a question I got last time. And so I'll use a few minutes to talk about what midterm 2 is. So that's the agenda for today. So let's get started with point number 1. And I know you have responded to your warm-up question, and so you're ready. And so you know what we are up to, the 3 tasks we have, plus talking about a little bit about midterm 2. So some languages are not Turing recognizable. Now that we know from the discussion we had last time, now that we know infinite sets can be of 2 types. Things that we can count, countable, things that we can associate with natural numbers in a way, and things that are uncountable. And so the reason that there are some languages that are not Turing recognizable is relatively simple. The underlying reason is because there are uncountably many, so uncountable, languages, but we have only countably many Turing machines. Both of them are infinite, but the first one is uncountable and the second one is countable. Therefore, we cannot find a mapping between Turing machines and all possible languages. That means there must be something that we are not able to recognize. That's the underlying idea. So we'll do this in a relatively easy way now for us. We'll make our job easier by taking the easier one first. So we'll first argue for the fact that there are countably many Turing machines. And then after we do that, we'll come back to the more difficult one. So to show that the set of all Turing machines is countable, we need to do a couple of things. First, we should go back and try to remember how the Turing machine discussion was. We spent like a series of 4 lectures. That was what we did, what we accomplished after we came back from spring break. We had Turing machines go through them. But one of the things that we know fundamentally about them is we can encode a Turing machine as a string. And in fact, what it takes is also like that. Its tape is going to work with a string. So to talk about how many possible Turing machines there are, we just need to observe the set of all strings, whatever the alphabet is. Sigma here is the alphabet. So whatever the alphabet may be, the set of all possible strings is countable. And I don't think that's too difficult for us to imagine and convince ourselves. So we can think about any alphabet we may have. So with only finitely many strings of each length, so that these strings, the star there, we have the sigma with the star. By now you all are experts. So that means we can have as many of these as possible. The length could be anything, including empty is what we mean. And so if we start to count this, which is the business we are in now, so we'll have strings of length 0, we'll have strings of length 1, we'll have strings of length 2, and so we can go on. When we have fixed the alphabet, sigma, then we can do this. And so for any alphabet then we can see that this is countable. Now, each Turing machine M then has got an encoding, as I just said before, has got an encoding in this into a string of this kind. That means we can, in this way, have the set of all Turing machines enumerated. In other words, Turing machine, the set of all Turing machines now, we can find a one-to-one correspondence with the set of natural numbers, and therefore this is countable. So task number 2, or among these 2 points that we want to make, the second one is already made. The first one is harder. And so let's try to show that the set of all languages is uncountable. If this was easy, I would have put it into this slide. We're not going to be able to do that. So we're going to need a couple more slides, but it is not very, very difficult, but we'll work our ways through. So we'll have a couple of slides now to show the first point. That is, we have uncountably many languages. We determined that we have countably many Turing machines. We will now show that there are uncountably many languages. By the way, as I always say, if you have a question as we discuss, you raise your hands or you unmute yourself and speak up. I'll try to keep an eye on the discussion on the chat, and so feel free to do it. It's clear now. So the warm-up question is answered, and it's clear for discussions of subject matter to our discussion here. Okay, so we're going to now argue for the fact that the set of all language is uncountable. So first, we observe that the set of all infinite binary sequences is uncountable. So we're going to do a little bit of a trick. This is some good way, I think, the book I have seen has to do. So as computer science, we should love binary numbers. Eventually, you know, everything boils down to zeros and ones, as you all know. But that's when we get to the machine itself. But the idea of having to work with binaries, you might have picked up from the exercise homeworks we do and so on, comes quite frequently. And so there are some times when this could be also used as a way to, as we will see here, to our advantage, to work with just these two. So we are going to work now with binary sequences, and let me define that. So I've got a binary sequence, means my alphabet is not zeros and ones, but now it is a sequence, and it is infinitely long. It is an unending sequence of zeros and ones. So that sequence I will call an infinite binary sequence. First, let's not forget what we are up to. We are up to showing the fact that all possible language that is uncountable is what we are up to. And so we're kind of finding a way now to get there to show that, right? So we are defining now, this is the infinite binary sequence, and we want to show that this is uncountable. And it is, because we have an unending sequence, and we are going to work with this. So let's call the set of all infinite binary sequences like this, we'll call it B. And so if you now kind of begin suspecting where I am headed, we're going to make use of this B. So we have now given a name for the set of all infinite binary sequences, and we'll call it a B. So what we'll do is we will show that B is uncountable. That means it is larger in size than what finite set, the infinite set of natural numbers would be. That's what uncountable would mean. So we can show that B is uncountable by using a proof by diagonalization. Now, so we are going to take advantage of what we learned last time. And that was why we said we are going to use the diagonalization method. Is important, what Counter did. And so we're going to prove by diagonalization, similar to the one that was used to prove the set of real numbers R is uncountable. So just remember how uncountable was done. We argued for a way to have, there is a function that will map our natural numbers to the set of real numbers. And then we said, no, there can't exist an F, because we constructed a particular kind of value. We called it X then, when we chose those digits in a careful way so that we would say this will never happen. There is no corresponding number in N that we can map it back to, and therefore that X cannot exist. That was the idea. And so we're going to try to do something similar to show that B, our newly defined quantity for us, which is the set of all infinite binary sequences, is large enough to be not on-to and one-to-one with the set of natural numbers. In other words, it's uncountable. And the idea will be similar to the diagonalization method we used for R. Okay, so that's our strategy. So we have come up with a way to show here is a B that is only working with zeros and ones, and it is infinitely long, and we're going to show that this is uncountable. So let L now be the set of all languages over an alphabet. So this B was our, as I said, our device. We are going to use it, but we are up for the task of showing that the set of all languages is uncountable. That is what we really wanted to show. So let's give that one also a name. Why not? And we'll call it L. Let L be the set of all languages over alphabet for a fixed alphabet, sigma. And what we will do now is what I just said. We will show that L is uncountable by giving a correspondence with B. We just, argued for the fact that B is uncountable. And so we will show that L is uncountable by finding a correspondence. So remember what the correspondence does. It is a one-to-one and on-to function. And so if we use a correspondence and say the set we are working with has a correspondence with the set of natural numbers, we are proving that it is uncountable. If we find some other guy that's uncountable, and then we say, okay, my third guy has got a one-to-one correspondence with this uncountable one, then we know the new guy is uncountable. That's what we are headed to doing. And so we'll give, for the sake of discussion now, we have a fixed alphabet, and that is sigma, and the set of all possible languages over this alphabet is called L, and we are going to give the strings that would come out of this alphabet S1, S2, and so we'll enumerate them in this fashion. So it's just a matter of notation for now. So each language that we pick from L, now it is a set of all possible languages, has a unique sequence. Now our device came. Our device was a binary sequence, and infinitely long, an unending sequence. So it has a unique sequence in this B, because we picked a language L, and B was the set of all possible binary sequences. Now it has got a unique one. And that one, we can define it in this way. And so this unique sequence in B that corresponds to the language A will have its i's bit, because now it is zeros and ones, of the sequence is 1 if we will call the i's bit of that sequence a 1 if Si, which is what we picked from this sigma star, belongs to A. If it belongs to A, we'll give it a 1. If it doesn't, then we'll give it a 0. So we've turned that sequence now, whatever that member was, into something that is only a 0 or a 1. 1 means it is a member of this Si is a member of this language that we picked, A. If it is not, then we will call it a 0. This has got a name. It's called the characteristic sequence of A. So in other words, we have turned A into a sequence after having defined what this S1, S2, and S3 are. So let me give you an example so that it will be easier. So we'll call, if A were the language of all strings starting with, now A is a language we're working with, so we can define any language we like. And so we are going to define a language A that would start with a 0. And the alphabet is a 0, 1. So we made our life easier now by making this language also to be on zeros and ones. We could have had something else, but it's easier for us to see. So the binary sequence now will come apparent, the sequence that we are going to define, the characteristic sequence. So sigma star now is when my alphabet is about zeros and ones, it's a sigma star will mean all possible strings that I can define over zeros and ones. I'll start with the empty string, and then I'll start with the strings of length 1. Strings of length 1 when the alphabet is 0 and 1 will be a 0 and a 1. Strings of length 2, I'll have a 0, 0, I'll have a 0, 1, I'll have a 1, 0, I'll have a 1, 1, and it will go on. And then I would continue with 3. So that sigma star is now all of the strings that I can imagine when my alphabet is zeros and ones. Now A is the language I just defined. I just defined the language that is all of them, all of these possibilities where they would start with a 0. And so among all these sigma star things, I will go over and find out a place where it starts with a 0. And so you can see that is what A is listing. So now I can define my characteristic sequence. And so the first one is not an empty. So Si is not a member of that sigma, and so it will be a 0. Every place where I wrote a value for A will be a 1, everywhere else will be a 0. So now I have a characteristic sequence to define A. For a fixed A, now I have turned it, which is now, well, it looks like this one is something that I can compare with what I called a B, which was an infinite sequence of sequence. So now I have turned it. That means I have found a function. I have found a function that takes me from this language, L, the one that I'm busy with, into B, which I have defined to be an unending sequence of zeros and ones. When the function is the characteristic sequence of A, then there is a one-to-one mapping, it is an onto, and there is a correspondence. Okay, now we established one big thing. The one that we just defined as a B has a way for us to map to this possible set of all languages. We know that B is uncountable, and therefore L is uncountable. That's the bullet point number 2. That means we have shown that the set of all languages cannot be put into a correspondence with the set of all Turing machines. The set of all Turing machines was countable. The set of all languages is uncountable because we managed to find a correspondence with this B of ours, which we know is uncountable. That means there is a mismatch between all the possible languages and all the possible Turing machines we have. All the possible Turing machines we have is countable. All the possible language we have is uncountable. That means there are some languages that are not recognized by any Turing machine. All right, so that was task number 1 of the 4 things we want to do. I'll save the discussion on midterm, not as a point. So let's have 3. Out of those 3, we have established 1. There are some languages that are not Turing recognizable, and we did not need to do any more exhibition. We will do that at the very end, but we showed that there are, and the way we showed is by simply, the crux of the matter becomes the set of all languages is uncountably many. The set of all Turing machines is countably many. And therefore, anything that is not included in there will be unrecognizable. Okay, the big theorem we had, or the big result we have, is that unlike the acceptance problem when our model is a DFG, unlike the acceptance problem when our model is a context-free grammar, when it is Turing machine, ATM is undecidable. And here comes the proof. Now we are going to start proving it. And so let's first appreciate that we just have argued for the fact that there are some unrecognizable languages. We just made that. So this is our second point. So we're going to work our way, and we're going to require a few slides. And so if you follow me along, it should not be too difficult to see, but it is a bit tricky. And so it's important that we follow along the steps, the arguments we make all the way through. Okay, so we'll assume now, and this has become now a way, I think, frequently occurring method of proof we have had so far for the theorems we have seen is proof by contradiction, especially negative result. This is not also too surprising if you have an impossibility result, like what undecidability means. Contradiction is a natural way to prove it. In fact, perhaps sometimes the only way to prove it. And so when it is a positive result, as I have repeatedly told you, when you can, a constructive proof, just demonstrating it, algorithmic construction proof will be what you will do because it is a positive result. There is something to be shown. Here it is the other way around and it's undecidable. So for the purpose of arriving at a contradiction, we will assume that ATM, in fact, is decidable. So we will suppose there is a decider. If it is decidable, there is a decider, and we'll give that a name, and we'll call it H. Suppose H is a decider for ATM, and let's W be any string that we'll be working with. So if it is a decider, that means H would hold, it will not loop forever, and accept if M accepts W, the input string, and H would hold and reject if M fails to accept W. Notice that we said if M fails to accept W, because at this point, what our M is, the Turing machine that we are working with, the one in ATM, and we don't know whether it is going to loop forever or reject, and therefore we will keep, at least say, H would hold and reject if M fails to accept. That's enough. So in other words, we are going to assume that H is a Turing machine where when it is given M, the Turing machine we are about to make a statement on in terms of whether it is decidable or not, and W, when the encoding of this, when this pairing is given, it will accept if M accepts it, and it will reject if M does not accept it. We don't, as they said, we can't go any further than this. So we have made an assumption that this is in fact decidable, and we called the Turing machine that would decide this one on H, and we described how it would behave. It would accept if M accepts W, and it would reject if M does not accept W. That far we have come. So now we're going to construct a new Turing machine. A new Turing machine, and we'll call this one D. And D is going to use H, which is what we just described, as a subroutine. That means it's going to call it. So this new Turing machine calls H to determine what M does in a very specific situation, when the input to M is its own description. So H took M, generally, whatever M is, and then we described it to behave, to accept if M accepts, and to reject if M does not accept. That's what H did. And so now our new Turing machine D will call H, but it is going to call it with a specific kind of input, and it will be not just any string W, but its own description. And this is the place where it might require your imagination, but you should not be too unsettled by this one. Having something that would take its own description might be thought of like what C compiler would do. And a compiler for C could be written in C itself. And so it's taken something of its own description in a way to say whether this program that somebody has written should compile or not, if it's okay, and turn it into a machine language, right? But it was written in the same language as what the compiler was written in. And so it's not fictitious, this thing to say the Turing machine M is taking its own description as an input. So once D has determined this information, it's going to do the opposite. And we are doing this because we are tasked, or we know where we're headed. We are headed to show some contradiction. And so one of the things we could do is come up with something that would make this thing explicit, that the contradiction actually shown. So D is going to behave in a way that is going to do the opposite. And so it does the opposite of what M, the Turing machine, would do. So it would reject if M accepts it, and it would accept if M does not accept it. So H was doing exactly the opposite of this one. So D, the one that's calling H, when the input is a description of the machine itself, and it will do the opposite in the sense that it would reject if M accepts, and it would accept if M does not accept. Okay, so if I put this one now in the form that you're familiar with, how a Turing machine is described, it would look like this. It's taking as an input the encoding of M, where M is a Turing machine. That is the input to our Turing machine D, and it's got two steps. First, it would run H, which we have described, on this input M and the description of M. So we've got a couple of Turing machines to keep track of here. And I will have one slide where I will put them all together so you will be saved at least this mental exercise. But keep thinking, and so have three Turing machines in your head. One, we have M, the one that we started with. We have another H that we introduced to do something, and it was behaving in a way that which we assumed is a decider. And so we would say, if M was accept, it would accept. If M was, we don't know whether it's halting. If it is not accepting, then we reject. That was what H did. And we've got a D that would do the opposite. And so these three things are happening now. So run H on input, but this D is not only doing the opposite, but it is also doing it for H on the specification of the machine M itself. So when we run H, we are running it on the input. The pair we give it is a Turing machine and the string is now a description of the machine itself. And that's what you see in that notation. So that was step number one for Turing machine D. So it would output, once it has run this, it would output the opposite of what H outputs. That means it would accept if H accepts, and if H rejects, it would accept. If H accepts, it would reject, and if H rejects, it would accept. So D does the opposite of H. So we have now come to this part. So let me summarize what we just said. So D, the Turing machine, the last Turing machine we have, on an input, which is a description of the Turing machine M, for which we are going to show at the end of the day whether this language or this membership was decidable or undecidable. That was what M was. So D, our machine, takes the description of M as an input, and it would accept if M does not accept, and it would reject if M accepts M. In other words, it's doing the opposite. That is what our Turing machine D does. Now, now we're going to get, okay, like Hunter was busy with these infinite numbers and weird things and came up with diagonalization. We're going to make ourselves now even a lot of more fun. So we now saw these three machines. For one of them, we gave the description of itself and so on. So now that we have D, why don't we exercise to see what D would do if it was given its own description as an input? And that is where a strange thing would happen. And so in that case, D is going to behave in a fashion that will just simply be impossible. D, when it is given its own description, the way we have specified it would say accept if D does not accept the description of B, and it would reject if D accepts D. Now you know what I mean. This is not going to happen. No matter what D does, it's being forced to do the opposite, which is just simply a contradiction. And therefore, the conclusion is neither the Turing machine D nor the Turing machine H can exist. And that will be the end of the proof for our purposes, that ATM is undecidable. And we constructed a sequence of machines to show that this one has arrived at a contradiction. So for what we really, really want, we have come to the end of the proof for this one. But I want to show you one more thing, and then the book does too. And let me, now that we have established this one, let me take a step further and then just review what we did with this proof, with H and the D and the M and having its own descriptions and so on. And so just review them. Just the fact that we review them itself is a good thing, but I have another important point to make with this review. So we assumed that there was a Turing machine H that decides for the purpose of arriving at a contradiction at the end of the day. And so that was our assumption. We used H to build a Turing machine D that takes as an input a description of the Turing machine M, where D would accept its input M exactly when M does not accept its input M. That was how D, the H was the Turing machine D was constructed using H. Finally, we ran D on itself. H, and we saw how D behaves, and then we ran D on itself. When we did that, the machine took these actions, which are shown in yellow, and we see that where the contradiction is coming. So H, the steps it would take would be, H would accept the description of the machine M and the input string W exactly when M accepts W. That far is fine. So H was doing what we would expect the decider to do, and there was no weird behavior. And then D would reject M exactly when M accepts M, because that's how we constructed D to behave in an opposite way. And then we supplied D with its own description, and there, right there, we arrived at a contradiction where D was doing the opposite of what it would do, which is very, very clearly a contradiction. When I motivated the discussion about having to say ATM is undecidable and we are going to need a method called diagonalization due to counter, and so we took a detour and talked about infinite sets and things like that. But we have said the diagonalization was useful for this proof, and if you followed me along, you would never see any diagonalization in any of these things we have done. And so we just had a bunch of machines, H, D, and M. And so we did, it was very convincing, but there was no place where there was any diagonalization. But I want to show you that. And then I want to show you that, and that will be the purpose of the next two slides, to just show there was hidden diagonalization in the proof. And it will become apparent if we were to dig deeper. And I think there is value in looking at that one. And so I'm going to have text here a bit to come. And so if you have wondered why I have all of a sudden changed the text color here, it's because I've got quite a bit of things to come, and I want it to be easier for you to see. No reason for any particular emphasis or anything. I just want to have one thing different from another color to just so quickly see a difference. So there was no diagonalization in the summary we just saw. We're doing fine on time. On the review of the proof we just went through, and we want to reveal that. We want to show that where the diagonalization was. So this becomes apparent when we examine a table. We never saw any table. We're going to come up with the table now. The tables of the behaviors of the Turing machines H and D. H was the Turing machine we introduced to come up with a contradiction, a decider, and D was the Turing machine we constructed to behave in an opposite way to arrive at a contradiction at the end. So that was what H and D were doing. And so we are going to work with a table, and in these tables, just like any table, we have rows and columns. So in this table, we will list all the Turing machines down the rows and all their descriptions, which is what these machines would take, H would take as part of its input, as an input will be a description of a machine, and we will have all the descriptions of the machine, the Turing machines, around the columns. Rows are the Turing machines, columns are the descriptions of the Turing machines, and all of them will be listed. Okay, we've got rows, we've got columns. What about the entries? The entries will tell us whether the machine in a given row accepts the input in a given column. Okay, now we have fully defined what this table is. And so the entry will be an accept if the machine in row I accepts the input. If it doesn't, then we will leave it blank. So if the machine accepts the input, we'll write the word accept, but we'll leave it blank if it rejects or loops on the input, because that's what would happen. So here is an example, and it's a cooked up example. It's the same example that is in the books. There is no reason why this particular machines would behave in this way. We just can't make up. And so this table would not have anything called reject. It will have only accepts, because when machine MI accepts a description of another machine MJ, we would say accept. If we don't have anything, then it is either holding, looping forever or rejecting. We will leave it blank. So we now have a table, good. Then the next thing we would do is we are going to have now this machine H now take and say how it would behave on when the machine we are looking at is MI, and the description we have is of Turing machine MJ. And so we have this combination. And now we have a table. Instead of having accepts on only empty places when we don't have reject and looping forever, the way we had constructed H was to actually avoid that, if you remember. So H was doing, it would accept when M accepts, and it would reject when M does not accept. That means it is either looping forever or rejecting. So this is what it is capturing. So now we have a table. Very good. So we started off by just have a simple definition for how to organize these things. And our goal is now to have all of these machines and all of this language possibly in one place is what the table's purpose is. And you know, I've already told you we are about to reveal that there was some diagonalization that has happened here. And so our H now has got entries defined everywhere in the table. So now let's consider where our D will show up. Our D is the one that helped us discover this contradiction, our decider D. And so it will show up in one of these machines, and its description will show up in one of the columns. And so let's see what that means. And so when we look at that reality, when the figure we just saw, where D is inserted into the picture, then we will see what would happen on the place where the machine is D, and the input is a specification of D. And so all these other ones would do how they were behaving, but exactly at that place, just like Hunter did with that example of construction X, we will have a place where we won't know what to do, to reject or to accept. And that is where the diagonalization is showing up. Okay, so I used three set of slides to show you that diagonalization was involved in the proof of the fact that ATM is undecidable. And this is secondary. The main important point is how the proof was there and to follow along those steps to arrive at a contradiction. And so we are now 100% convinced that ATM is undecidable, and we would know how to prove it, at least at a very high level, the steps involved in doing it. All right, task number 2 is done. So we are now going to show, give an example. So the first thing we did, of the 3 things we did, was to show that there are some languages that are not Turing recognizable. The second thing we did was to prove, we knew, or we have agreed, or we have declared that ATM is undecidable, but today we proved that it is undecidable, and we show some connection with diagonalization. The third thing we want to show is, give me one example, please, one example of a language that is not Turing recognizable, that is not Turing recognizable. In other words, is Turing unrecognizable. That's what we want to do. And we will do this by showing a result that is even more general. So actually, the exhibition, the one that we will give this example, will just be something that would follow from here. There will be a corollary. That's exactly what it is. And so we'll show something bigger. And that something bigger is this theorem. And this theorem will talk us about a language that is Turing recognizable, and we're talking about a language that is the complement of this language. And so when a language is, it is called this is a definition, is called co-Turing recognizable if it is a complement of a Turing recognizable language. So the language, it is Turing recognizable with plenty of examples of those. If it is the complement of the language, if a language that we're looking at is the complement of a Turing recognizable language, we'll call it co-Turing recognizable. This sort of things sometimes bother me, so they're not all that important. It's just because you want to write shorter later on. So we gave it a name. So the complement of a Turing recognizable language is called co-Turing recognizable. Great, that's it. That's what the definition says. The result or the theorem is a language is decidable if and only if it is Turing recognizable and co-Turing recognizable. So we just defined what co-Turing recognizables are. So the theorem could actually could have been equivalently, or in other words, that's the I-O-W there. In other words, be described like this. A language is decidable exactly when both the language and its complement are Turing recognizable. When both of these are true, when a language is Turing recognizable and its complement is also Turing recognizable, then the language is decidable. And this is going to work both ways. And so we're going to prove both directions. And so we'll go with the first direction that usually kind of may confuse you, but the first direction comes in this backward way. So if A is decidable, then it is not difficult for us to see that both A and its complement are Turing recognizable. Why? Because any decidable language is Turing recognizable, and the complement of a decidable language is also decidable, because whatever we are doing with accept, we will reject. Whatever we did with reject, we would accept. Otherwise, there isn't any difference. And therefore, if a language is decidable, then both its the language itself and its complement are Turing recognizable. That's easy. The second part is not so easy. The second direction. That means if both A and its complement, and I'm using this thing, I could not put the bar just over the top of A, and so that's why you see this weird notation. So if both A and its complement A bar are Turing recognizable, then the language has to be decidable, is what we want to show. So we will show this we did a couple of steps. So we'll have two machines. We'll call the machine that recognizes A, we'll call it M1, and we'll call the machine that would be a recognizer for A complement, would call it M2. So if both A and A complement are Turing recognizable, that means I have a machine that would recognize A, a Turing machine that would recognize A. I have a Turing machine that would recognize A complement. I will call the Turing machine that recognizes A, M1. I'll call the Turing machine that recognizes A complement, M2. And so what do? Then I'm going to come up with another machine called M that will be a decider for A. And that's what I will show you in this slide. So M, my new now, will take on input W, and it would run both M1 and M2 on the input W, and it will do this thing in parallel. If M1 accepts it, that means the one that is accepting A1, the language, it would accept. If M2 accepts it, then it would reject. M2 was the one that accepted the complement, and therefore it would reject. That would make sense, right? And so what does it mean when we have two machines and I'm running them in parallel? It means that M, my Turing machine now, has got multiple tapes. And thanks for the discussion we had on the second day of online lecture, I think it was, when we had these variations of Turing machines. We said we could have multiple tapes on a Turing machine, and this is not going to change how powerful they are and so on. So we can now say M has got multiple input, or two tapes. And so one of the tape would be used for M1 and the other one would be used for M2. And therefore we're safe when we say run M1 and M2 in parallel. What we mean is that we are going to have a Turing machine that has got two tapes. And then the next thing to do will be to show that M, the Turing machine that we just constructed, would decide A. So it will take any string. And if we take any string, by definition, it's either in A or it's in complement. Where else can it be? So if I take any string, it will belong to either A or A complement. Therefore, either one of these two must accept W. And if because M holds whenever M1 or M2 accepts. That's how the M was constructed. M always holds, and so therefore it is a decider. And therefore, we could say, and we could in addition say it accepts all strings in A and rejects all strings not in A, which means strings that are in A complement. So then M is not only a decider, but it is a decider for A, and therefore A is decidable. Okay, so what did we do? We just showed the other proof, the other direction of the proof. So a language is decidable if and only if both the language and its complements are Turing recognizable. Then we have a new result that showed us or characterized what Turing decidable languages are. Turing decidable languages are the ones for which the language and its complements are both of them Turing recognizable. That means now the complement of ATM, the one we showed to be undecidable, has got a complement. Why not? It has a complement. That cannot be Turing recognizable. This is a corollary of the result we just showed. Why? Because we know ATM is Turing recognizable. We showed that Monday, long time ago. And we know that if ATM complement also were Turing recognizable, then ATM would have been decidable. But we just showed today that ATM is not decidable. So that means one of them will not be Turing recognizable. And we know that ATM is Turing recognizable. So the only thing that's left now is for ATM complement not to be Turing recognizable. So at the beginning of this lecture, we said we'll do three things. One of them was to say, generally speaking, there are some languages that are not Turing recognizable. We did that. We did that by enumerating, by showing the correspondence with a particular kind of B. And so we said there are some languages that are not Turing recognizable. Now we have a concrete example of a language that is not Turing recognizable. And that language is the complement of ATM. ATM is the decision problem we had, or the acceptance problem we have, and its complement would be the one that is a negation of it. That one is not Turing recognizable. ATM is Turing recognizable. Okay, so that would complete what I wanted to do in terms of things to cover. And we do have 4 minutes, and so I want to tell you a little bit about midterm 2. So first, it's going to be take home. The exam will be released Friday when we meet in class, 10 a.m. And it will be due, you will get 24 hours. It will be due on Saturday, but I have a grace period of 4 hours. So I would have called it 28 hours. It will get it out in class. You will see what it looks like. You'll get a chance to ask me if you need clarification questions and so on, but that will happen on Friday, and Saturday is when you submit it, by Saturday. And I have 24 hours, would have been 10 a.m., but we'll go up to 2 p.m. on Saturday. Okay, so this is the format, this take home, you've got this. It doesn't mean it's going to take all of those 24 hours. So this is, you work on it and at your own time, but you will have to submit by this time, and it will be in PDF. You could either write your solutions, type up your solutions, get a PDF, or scan like what you would have done with homework, but it will be submitted in PDF. And so we will meet on Friday for class. I will introduce the problems, and so you will get to know them. But if you have clarification questions, or if there are places where you want me to review or something, we could use that. And so we'll meet on Friday. Now, there was a question I got, and I told you what topics we would cover, and that's what we have. Here. So the topics that will be covered will be primarily what we finished in the Turing machine, and among the decidable language in the chapter 4 about these decidability issues. Undecidable, what we just finished on Wednesday and what we did today, will not be in the midterm, but it will be the decidable portions. So only that portion. Other than that, we will go back before spring break and talk about, or we'll look at context-free grammars. That will be section 2.1 in the book, and push-down automata. That will be section 2.2. So if I put this chronologically, it will be context-free grammars, push-down automata, Turing machines, and decidable languages. And I have listed the section numbers in the book, and I've tried to remind you which lectures cover them when you review things. I think this will be helpful as you prepare. So think of this week as your preparation for your midterm, but then you will get a chance to ask questions on Friday as well. I see a question, how difficult it will be. It's going to be different slightly from how your homeworks would be, but I would not put it a whole lot more difficult than what homeworks would be, but they would be fewer. There will be 4 questions. There will be 4 questions and they will have ABCs. And so the topics that I have listed here is a good indication of what they would be covering. And so they will be creative. And so they will require, if you don't understand the material, you will not be able to answer them. So that much is clear. It's an open book, basically, what take-home exam would mean. So I think a way, if you want to calibrate it, is to say the homeworks are one good indicator. But you've had time over a long time, but this one will be something you'll prepare for and solve in the time that you are given. So you work on it and solve on the time when you are able, in an asynchronous fashion, in a way that would suit you, but it's not going to require all those 24 hours, basically. And it's not going to be something that I would say is very different from what homework should be. You'll see the exam out when we come to class. We may not need the whole class. It depends on the discussion we will have, but it will be clarification. I'm not going to solve those problems, obviously. And I'm going to trust that you will do your own work, and so I'll talk about that on Friday. Okay, this is where I want to stop. It is 11. Any questions for me? Were you able to follow me along with the discussion on undecidable problems? How long would you expect it to take? If you know the material, it should not take more than a couple hours, 3 hours, I would say, 2-3 hours. But Friday will be a good time to ask those questions. Okay, then I will stop here and I will see you all on Friday. See you then.